Welcome to this coding problem walkthrough. In this session, we'll explore problem number 1839, longest substring of all vowels in order. We'll break down the problem, discuss possible approaches, and ultimately work toward an efficient solution. Let's dive in. In this problem, we are tasked with finding the length of the longest substring in a given string word that contains all 5 vowels a, e, I, o, and u in order and exactly once. This means the vowels must appear in the sequence of before e before I, and so on, up to u. For example, a substring like aiou satisfies these conditions, as does aiou, because it still maintains the correct order. However, substrings like uaio or aoiu are not valid because they either contain vowels out of order or are missing some of the required vowels. The goal is to return the length of the longest valid substring, or 0 if no such substring exists. To solve this, we need to carefully analyze the order of vowels in the input string while ensuring our solution is efficient enough to handle strings of up to 100,000 characters. Let's look at an example to understand this better. Suppose the input string is aiou. The output for this example would be 13. This is because the longest valid substring is aiou, which contains all 5 vowels in the correct order a, e, I, o, u. Notice that this substring satisfies the condition of having each vowel appear in order and at least once. Other substrings in the input may contain vowels but fail to meet the requirements, either because they break the order or do not include all 5 vowels. Now, consider another example where the input is aiou. Here, the output is 5. The longest valid substring is aiou, which contains all 5 vowels exactly once and in the correct order. While other parts of the string contain vowels, they do not meet all the rules for a valid vowel substring. For instance, some substrings might repeat vowels excessively or mix up their order, but only aiou forms a valid sequence. Finally, let's examine a simpler case where the input string is just a. In this case, the output is 0 because the string contains only one vowel and does not include all 5 vowels in order. This highlights an important edge case: if the input string lacks all 5 vowels or if the vowels are out of order, the result must be 0. Additionally, since the string can be very long, up to 100,000 characters, our solution must process the input efficiently without missing edge cases such as repeated substrings or missing vowels entirely. To begin tackling this problem, we could consider a brute force approach. The intuition here is straightforward: generate all possible substrings of the input string and check each one to see if it meets the criteria of being a valid vowel substring. A valid substring must include all 5 vowels a, e, I, o, u in order and contain only vowels, with no extra characters. To do this, we can use a helper function that validates each substring based on these rules. If a substring is valid, we update our maximum length. However, this approach comes with significant computational drawbacks. Generating all substrings requires n² time, and validating each substring could take up to k, where k is the substring length. This leads to a total worst-case time complexity of n³. For large inputs, such as when the string length reaches 10,000, this method becomes highly inefficient and impractical, making it unsuitable for this problem. A more efficient solution is to use an optimized sliding window approach. This method leverages 2 pointers and a state tracking variable to process the string in a single pass. The key insight here is that a valid substring must contain vowels in strict order, a, e, I, o, u. If the order is violated or a non-vowel character is encountered, the state and sliding window are reset. The state variable is used to track our progress through the vowel sequence. For example, encountering a sets the state to 1, e advances it to 2, and so on, until u completes the sequence at state 5. When the state reaches 5, it means we have found a valid substring, and we update the maximum length. Using 2 pointers to define the sliding window, we traverse the string while maintaining the state and ensuring the substring remains valid. This approach allows us to efficiently identify and track valid substrings without redundant checks. This sliding window approach is not only conceptually straightforward but also highly efficient. In terms of time complexity, it processes each character of the string exactly once, resulting in n time complexity. The space complexity is 1, because we only use a few variables, such as the state and pointers, without requiring additional data structures. These characteristics make this approach ideal for solving the problem efficiently, even for large input sizes. The method's efficiency stems from its ability to avoid unnecessary computations by promptly resetting whenever an invalid character or sequence is encountered. This ensures that we focus only on valid substrings and skip over invalid ones as quickly as possible. Given the problem's requirements, the sliding window approach emerges as the optimal solution. Its linear time complexity ensures scalability for large inputs, while its constant space usage keeps memory overhead low. The key realization here is that by focusing solely on the sequence of vowels in strict order and resetting the state whenever necessary, we can efficiently solve the problem without redundant computations. Compared to the brute force method, which is computationally expensive at n cubed, the sliding window approach is exponentially faster and handles edge cases gracefully. Alternative strategies, such as dynamic programming, are unnecessary because the problem's constraints can be addressed with this simpler, greedy approach. Overall, the sliding window technique balances efficiency, clarity, and correctness, making it the best choice for this problem. To approach this problem, we are tasked with finding the longest substring in the given string word that contains all 5 vowels A, E, I, O, and U in their correct order. Each vowel must appear exactly once in the substring, and the sequence must be maintained. One possible way to solve this is by using a brute force method. The idea behind this approach is to systematically generate all possible substrings of the input string and then check each one to see if it meets the criteria. While this is not the most efficient solution, it provides a clear way to explore all potential answers. To break it down, the first step is to generate all substrings. This involves iterating through all possible starting indices I of the string and, for each starting index, iterating through all possible ending indices j where j is greater than I. From this range, we extract the substring word, ij plus 1, and prepare it for further evaluation. Once we have the substrings, the next step is to verify if each one is a valid vowel substring. To do this, we need to check that the substring contains all 5 vowels in the correct order. This can be achieved by iterating through the characters in the substring while using a pointer to track the current vowel we expect to see. If a character matches the expected vowel, we move the pointer forward to validate the next vowel in the sequence. If all 5 vowels are successfully matched by the time we finish iterating through the substring, it is considered valid. Now, to find the longest valid substring, we maintain a variable called longest. Each time we identify a valid substring, we compare its length to the length of the current longest substring. If it is longer, we update longest. Finally, after checking all substrings, we return the value stored in longest. However, this method is computationally expensive. Generating all substrings requires n squared time, and verifying each substring might take k, where k is the length of the substring. In the worst case, this results in an overall time complexity of n cubed. This brute force approach, while inefficient, provides a few key insights. First, generating all possible substrings ensures that every potential solution is considered. While this is not optimal for performance, it is thorough and guarantees correctness. Next, maintaining the order of the vowels A, E, I, O, U is crucial to solving the problem. This ensures that substrings like A, I, O, U are valid, while substrings such as A, U, I are not. Additionally, by tracking the longest valid substring, we ensure that we return an optimal solution. Any substring that meets the criteria but is shorter than the current longest is discarded. Finally, we must carefully handle edge cases. Examples include strings that do not contain all the vowels, such as A, B, C, D, E, which should result in an empty output, or strings with repeated vowels in the correct order, like A, O, U, U, where the entire substring might be valid. Similarly, very short strings, such as A, E, or U, need to be handled without errors. To implement this algorithm, we rely on a few key data structures. Strings are used to extract and store substrings since they allow us to easily access individual characters and manipulate portions of the input. A pointer is also essential for tracking the current vowel during the validation process. This makes it efficient to traverse the substring while ensuring that the vowels appear in the correct order. However, the brute force approach can be optimized for better performance. One way to do this is by using a sliding window technique. Instead of generating all substrings up front, we can dynamically adjust the window size and check substrings on the fly, reducing redundant computations. Additionally, hash sets can be employed to quickly validate the presence of vowels within a substring. These optimizations significantly reduce the time complexity, making the algorithm more suitable for larger input strings. By balancing correctness with efficiency, we can refine the solution to handle a broader range of scenarios effectively. Here, we define a class called solution and implement a method named longestBeautifulSubstring. Inside this method, we first establish a string vowels containing all vowels in order, a, e, I, o, u. We then initialize three variables, max_length to track the length of the longest valid substring, current_length to keep track of the current substring length, and vowel_index to monitor which vowel we are expecting next in the sequence. Now, using a for loop, we iterate through each character in the input string word. If the current character matches the vowel at the current vowel_index, we extend the length of the current valid substring by incrementing current_length. If the character matches the next vowel in sequence, indicated by vowel_index +1, we advance the vowel_index and also increment current_length. However, if neither condition is met, it means the sequence is broken. In this case, if the character is a, we reset current_length to 1 and vowel_index to 0, since a new valid sequence could potentially start from this point. Otherwise, we completely reset both current_length and vowel_index to 0, as the current character doesn't contribute to any valid sequence. Finally, whenever the vowel_index reaches 4, indicating that we've successfully passed through all vowels in order, we update max_length to store the maximum length found so far. At the end of the function, we simply return max_length, which holds the length of the longest substring where all the vowels appear in order. This ensures that the result reflects the length of the largest valid sequence found within the input string. With this, the implementation is complete, and the function efficiently evaluates the input for the desired condition. Here, we define the longestBeautifulSubstring method, which takes a string word as its input. The goal is to find the length of the longest substring where all vowels appear in order and consecutively. We start by defining a string vowels containing a, I, o, u, as these are the vowels we need to check for in sequence. We also declare variables, maxLength to track the maximum length of such a substring, currentLength to track the length of the current valid substring as we iterate, and vowelIndex to keep track of which vowel in the sequence we are currently expecting. Next, we use a for loop to iterate through each character of the input string. If the current character matches the expected vowel based on vowelIndex, we simply extend the current substring by incrementing currentLength. However, if the character matches the next vowel in the sequence, we increment vowelIndex and also increase currentLength, effectively moving forward through the vowel sequence. If the sequence breaks, we reset currentLength and vowelIndex. If the character is a, we restart a new potential substring, since valid sequences must begin with a. Otherwise, we reset completely to start fresh for the next potential sequence. Now, we include the condition to check whether the current substring contains all 5 vowels in order. If vowelIndex reaches 4, meaning we've successfully traversed the sequence up to u, we update maxLength by comparing it with currentLength. This ensures we always store the length of the longest valid substring found so far. After the loop completes, we return maxLength as the result. This implementation effectively handles the problem by iterating through the string once, maintaining a running count of the valid substring length and only updating the maximum when all vowels are present in the correct order. The use of vowelIndex allows us to efficiently track the sequence, and the resets ensure that broken sequences do not interfere with valid ones. In this example, we start by initializing the variables needed for our algorithm. The vowel string represents the sequence AIOU that we are trying to match. We set max_length to 0 to keep track of the longest valid substring found, current_length to 0 to measure the length of the current substring, and vowel_index to 0 to track our progress in the vowel sequence. As we process the input string, the first character is a, which matches the current vowel in the sequence at vowels, vowel_index. So, we increment current_length to 1, and our variables reflect this progress. Current_length is now 1, and vowel_index remains 0. The next character is E, which matches the next vowel in the sequence at vowels, vowel_index +1. This means we move to the next vowel, updating vowel underscore index to 1 and incrementing current underscore length to 2. Continuing this process, the character I matches the next vowel in the sequence, so we increase vowel underscore index to 2 and current underscore length to 3. However, when we encounter the next it breaks the sequence since it does not match the expected vowel at the current index, and this triggers a reset of the substring calculation. At this point, because the sequence was broken by the character we reset current underscore length to 1 and vowel underscore index to 0 to restart the process from the beginning of the vowel sequence. As we keep processing the input, the substring eventually aligns with the full sequence AIOU toward the end of the string. This valid substring allows us to update max underscore length to 5, which represents the length of this valid sequence. After completing the traversal of the input string, we finalize the result of this example with max underscore length equal to 5. Now, moving on to the second example, we initialize the same variables as before. Vowels is set to AIOU, and both current underscore length and vowel underscore index start at 0. The max underscore length is again initialized to 0 to track the longest valid substring. In this second example, we begin processing the input string. The first character, matches the first vowel in the sequence, so we increment current underscore length to 1 while keeping vowel underscore index at 0. The next character, matches the second vowel in the sequence, so we increment current underscore length to 2 and advance vowel underscore index to 1. However, the subsequent does not match the next expected vowel in the sequence, which is I. This breaks the sequence, so we reset both current underscore length and vowel underscore index to 0. As we continue processing the string, the substring fails to form a complete valid sequence of AIOU. This means no valid substring containing all vowels in order is found in this example, leaving max underscore length at 0. In the third example, we analyze a longer input string that contains multiple occurrences of the sequence AIOU. After initializing the variables, we process the string character by character. The first valid substring, AIOU, is identified early in the string. As each character matches the expected vowel in the sequence, we increment current underscore length and advance vowel underscore index. By the time we reach the U, we have a valid substring with current underscore length equal to 5, and we update max underscore length to 5. After a break in the sequence, we restart from A and find another valid substring, AIOU, later in the input. Once again, current underscore length reaches 5, and since this adds to our previously found valid substring, we update max underscore length to 10. This represents the combined length of the two valid substrings in the input. To summarize, the solution relies on tracking the current index in the vowel sequence with vowel underscore index and resetting the substring whenever the sequence is broken. The algorithm ensures that only valid substrings containing all vowels in the correct order are considered. Each time a valid substring ends with the vowel U, the max underscore length is updated if the current substring's length is greater than the previous maximum. This approach efficiently processes the input while maintaining the constraints of the problem, ensuring that only the longest substring of vowels in order is returned as the result. In this solution, we process the input string word in a single pass, which means we iterate through each character exactly once. Let's say the length of the string is n. For each character, we perform a few constant time operations. For example, we check if the character matches the current vowel or the next vowel, update variables like current underscore length and vowel underscore index, or compute the maximum length using the built-in max function. All these operations take O1 time individually. Since the loop runs n times and each iteration performs only O1 work, the overall time complexity of the solution is O(n). This makes the algorithm very efficient in terms of time, as it scales linearly with the length of the input string. Now, let's analyze how the time complexity holds up in different scenarios. In the best case, if the sequence breaks immediately for every character, such as when the input is BBB, the loop still processes all n characters, so the time complexity remains O(n). For the average case, given a random string of length n, the algorithm still iterates through each character exactly once, leading to O(n) time complexity. In the worst case, if the input string is made up entirely of valid sequences of vowels, like AIOU, the loop still processes each character once without any additional overhead, maintaining O(n) complexity. For space complexity, the algorithm uses only a fixed amount of memory. This includes the string vowels of length 5, and 3 integer variables, max_length, current_length, and vowel_index. Since no additional data structures or recursive calls are used, the space complexity is 1, irrespective of the input size. Let's compare this optimized solution to a brute force approach. In a naive method, you might generate all possible substrings of the input string and then validate each one to see if it's a valid beautiful substring. Generating all substrings of a string of length n results in n squared substrings. Validating each substring could take up to n time, especially if the substring is as long as the input string. Combining these, the total time complexity of the brute force approach would be n cubed. In contrast, this optimized solution eliminates the need to generate substrings. By using a single pass and efficiently tracking the sequence with constant space, we reduce the time complexity from n cubed to n, and the space complexity from n, which would have been needed to store substrings, to 1. This is a significant improvement in both time and space efficiency. Finally, let's solidify the reasoning behind the big O complexity. With n representing the length of the string, the for loop runs exactly n iterations. Each iteration involves a constant amount of work, such as comparisons, updates, and assignments, all of which are 1 operations. As a result, the total work done is proportional to n, giving a time complexity of n. On the space side, the algorithm only uses a fixed number of variables, regardless of the input size. This means the space complexity is 1. To summarize, this optimized solution is both time and space efficient, achieving n time complexity and 1 space complexity, which is a significant improvement over the brute force approach. This efficiency makes the algorithm well suited for handling large input sizes effectively. When working on this problem, there are a few common mistakes that can trip you up. First, overlooking edge cases is a frequent issue. For example, you might forget to test scenarios like an empty string, a single character string, or a string without any vowels at all. These can lead to runtime errors or incorrect results. To address this, it's critical to include these edge cases in your test plan and explicitly handle them in your code. Another mistake is implementing an inefficient brute force solution. Generating all possible substrings, which takes n squared, and then validating each one, which adds k for length k, results in an overall complexity of n cubed. This approach won't scale well for large inputs. Instead, you can use techniques like sliding window or prefix sums to optimize and avoid redundant computations. Lastly, assuming that the input string contains only lowercase vowels is a common oversight. If the problem allows uppercase vowels as well, your solution might fail. A simple fix is to normalize the input by converting all characters to lowercase, or explicitly handle both uppercase and lowercase vowels in your logic. Another frequent pitfall is misinterpreting the problem statement. It's important to clearly understand what qualifies as a valid substring. For instance, does the substring need to contain all vowels, and do they need to appear in order or be contiguous? Misunderstanding these nuances can lead to incorrect logic in your solution. The best way to avoid this is to carefully read the problem statement and clarify any constraints or definitions before diving into the implementation. Additionally, overlooking constraints on the output can cause issues. For example, you might forget to consider limits on the maximum length of the substring or the required format for the result. To prevent this, ensure that your output adheres to the problem's constraints and matches the examples provided in the description. Validating your results against these expectations is a critical step in ensuring correctness. Understanding how substring-related problems are typically tackled can give you an edge during interviews. Recognizing patterns is key, as many such problems can be solved using sliding window or two-pointer techniques. Developing the ability to quickly identify when these approaches apply is invaluable. Interviewers often expect you to start with a brute force solution and then optimize it, so be prepared to discuss the trade-offs involved and clearly explain why your optimized solution works. Edge cases are another area of focus during interviews. They help assess the robustness of your solution, so always make it a point to ask clarifying questions about constraints and edge cases before you begin coding. Lastly, communication is vital. Clearly articulate your thought process and reasoning, especially when you're justifying optimizations like reducing time complexity from O(n) cubed to O(n). To build a strong foundation, you can also practice related problems like longest substring without repeating characters, minimum window substring, or others that involve similar techniques. To approach this problem effectively, there are several alternative strategies you can consider. The sliding window technique is a popular choice. Here, you maintain a window containing valid characters and dynamically expand or contract it to find the desired substring. While this method is efficient with a time complexity of O(n), it requires careful attention to how the window is updated. Another approach involves using prefix sums. This involves pre-computing the cumulative count of vowels, which allows for quick-range queries during the problem-solving process. While this method simplifies certain queries, it does require extra space for the prefix sum array. Finally, you could use a combination of a hash map and two pointers. The hash map tracks vowel counts while the two pointers adjust the boundaries of the substring. This approach strikes a balance between speed and space efficiency, but it can be tricky to implement correctly. Each of these methods has its trade-offs, so the best choice depends on the specific constraints and requirements of the problem. Great job following along. We've covered the key insights and approaches to solve this problem. Remember to keep practicing similar problems to strengthen your skills. Thanks for watching, and I'll see you in the next video. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!